So, aromatic reactions. That slide should effectively be memorized. Okay. The rest of the lecture that we went through was looking at all the details, mechanisms, pieces behind it. But if you memorize that, you're probably pretty square when it comes to EAS, okay, or the aromatic stuff. Make sense? Okay. Which then means we can talk about polymers. Yay, polymers. Okay. First thing we'll address is how you will see them show up. Polymers are extended structures, so there's lots of repetition. Because that repetition in each of these is actually relatively small. If we look at just that first one, what we're talking about for that polymer is probably on the order of thousands of carbons. Okay? That's going to be a horrible structure to draw. So what I want to do is come up with some kind of shorthand to represent that entire structure, right? Or the majority of it. So how could I do that? Well, I want to find the smallest repeating unit within that structure. And we'll start just with this one. So where's the smallest repeating unit?
The CH3 to the CH2.
Right. So there's a suggestion for a CH3 to a CH2. Okay. So if this is the repeating unit, if I copy and paste this, does this copy and paste across? Is the very next thing a CH3? No, it's a CH2. So the CH3 to the CH2 isn't going to be a good repeating unit to pick up because as I copy and paste that either direction, I'm not going to have a CH3 through the middle of that structure. Does that make sense? Okay, sorry, I talked over you.
So then you would do the CH3 and then two CH2s? Or
okay, CH3, CH2, CH2. Copy and paste. What's the very first thing we should copy and paste right there? A CH3. Can't have a CH3 though.
Just CH2.
Right? So instead of including the CH3, what if we just did the CH2s? The very next thing I would paste here would be CH2. And the next thing? CH2. There's that unit. What's the next thing I'd put in? CH2. The next thing? CH2. Okay? So one of the things that can be misleading when we look at our polymers is we will zero in on these caps. Okay? Remember, this is thousands of carbons. Those caps make up 2 of the thousands of carbons. Is that a significant thing to include in your polymer structure? No. Is it significant to how the reaction works? Yes. Okay, or how it started and ended, but it's not significant to what the polymer is. Does that make sense? Okay, so if we ignore those caps, we kind of just have everything in the middle. So let's summarize out, and we said that we wanted CH2, that CH2. Because that's ugly to write it, I'm not going to write it there, but what I will do is now put brackets around that section. Notice the parentheses are going through the bond. They're not going through atoms. Okay, everybody see that? So now when we copy and paste, theoretically either direction, this structure continued on. Okay, that would work as a repeating unit. Okay, is there another repeating unit I could have done? Middle 2 CH2s, is that any different than what we've already got boxed in? No. So that's not going to count. That's the exact same thing.
Just one CH2.
How about I do just one CH2? If I go to the right, what would I expect to see? CH2. If I go to the left, what would I expect to see? CH2. Did that work? Yeah. So that is a repeating unit. So I could also go through and show it like this, with the parentheses just around that. Okay? Kind of, sort of? All those other letters are bothering me, so I'm going to erase all that. Okay? If I now wanted to represent how many times it was repeated, all I'd have to do is specify in the lower right-hand corner, like we do with, say, water. How do I know that's water?
2.
I need a 2 in the lower right-hand corner to say there's 2 hydrogens. How many times do I want the polymer to repeat? Well, if it's 1,000 times, There we go. And I'm now representing how many times that thing repeats out. Does that make sense? Okay. I can do the same thing with the other one, if there would be the same polymer. Okay. Oftentimes we won't actually specify that number and we'll just leave it empty, or we could also throw in n for number. Okay. It doesn't have to be n, but typically n is what's thrown in there. It could be x, y. It's really just representing any variable. Make sense? Okay. So now the next layer that we can add on top of this is one of those better than the other for our representation of that polymer. One is shorter than the other. The blue one is a shorter representation of that entire molecule. Okay? So which would you prefer to do? A short OChem class or a long OChem class? You'd probably want short, right? We want things to happen faster. The blue one is the standard kind of IUPAC notation. The problem with that standard is that most people think that that is an awful idea. Do you think you would have done well if this had been an 8-week class as opposed to a 16? Most people would agree that that is an awful idea to try and cram it all into one go. Okay? It's still possible it could still do it, but it's not the greatest representation of it. The same kind of thing is happening here. IUPAC says you got to show it blue, and everybody else says that's a stupid idea. Okay? Why are they saying it's a stupid idea? What we're trying to represent is the smallest monomer that went into this. What are the pieces that were added to this structure? If we look at IUPAC's notation, we're saying CH2. Okay, well, to make each of those bonds going out either direction, we'd have to supply electrons out one end, and we'd have to supply a place to put the electrons out the other. Having a single carbon that is able to do that, not likely. Okay? So the ability to make that as the monomer to build that polymer, not very good. Okay? What would be a more likely way to build that? Well, I can take this CH2, bond it to that other CH2, and I'm going to still have the same issue. I still need a positive and a negative. Like, well, that's equally bad, right? Why not?
They're on different because one carbon can take up one charge and another carbon can take up another.
So we could look at, distribution of those charges. Yeah, that could help. So we're hearing alkene being floated out there. I don't see a pi bond. If you draw the resonance structure of the electrons going in to share those, we've generated an alkene. Is an alkene a stable starting material? Yes. I can get alkenes and I can force this reaction to run. Okay? So the red parentheses is a better representation of that polymer because it allows us to see the monomer that built that polymer. Does that make sense? Okay. That's the intent behind the red one. Most chemists that don't deal with polymers often will stick with the red notation. Those that deal with lots of polymers will stick with the blue notation. Okay? And it just comes down to a comfort with that science. Kind of make sense?
If
Okay.
you were asked on an exam what the shorthand is, would you be given both as a possible answer?
No. Yeah. So for those of you that couldn't hear that, you would not be, if you were asked for the shorthand, we wouldn't give you both. Okay? That's now digging way too much into the polymer science behind it and the polymer rules, and that just isn't covered in enough detail in an organic chemistry class. If you are a polymer chemist in a polymer class, hell yes. You're not, so don't worry about it. Kind of make sense? Okay. So let's switch up that top one. Let's go through and, well, that's dumb. What if we move to that next one? Where's our shortest repeating unit?
Just purple.
I know what you're referencing in the isopropyl. The propyl does become a questionable statement to make, right? Because the propyl, we might get something more like our straight alkane. By throwing in the iso, you're now saying one of those carbons is left off as a piece that's not being part of the polymer chain. Okay? So I understand where both of you are coming from in that reference. I would argue the isopropyl was probably a better name. Both cases, I'd say they're wrong. Okay? But it allows us to zero in on those pieces. Okay? And that's the primary goal. Could I have done that in blue? Yeah. Is there one that's more correct than another? Yes. That's the role of IUPAC. Do you care? No. Make sense? If we were to split that apart, same deal. What we're looking at is how that polymer extends outwards. One end would have to be negative. The other end would have to be positive. What would be a likely starting material? The alkene. Make sense? So our polymer is forming through that alkene backbone. Good? Okay. Let's make it a little bit more complex. We'll go back up to that alkane one. We'll do... Oh, I'm probably going to butcher this, but close enough. What do you see now? Somebody think they know where the monomer is. Yeah? Okay. Does everybody agree? What do you mean mostly?
There's another one you could have done.
There's another option, yes. There's also another problem. If I take this structure and I copy and paste it here, right? The very first thing I should encounter would be a carbon with a methyl. What's the very first thing I encounter outside the parentheses? A CH2. Was this copied and pasted appropriately? No. So all we have to do to fix that, bring in that next carbon. Now it'll copy paste out nicely. Everybody see that? Okay. So this does work as a potential monomer out. So if we looked at this, we'll call this a purple. I think I can get away with color coding it this way. Okay. Where, whoops. These carbons have to be our opposite charges, right? One would have to be positive, one would have to be negative. We don't have that alkene option anymore, right? So how did we get that? Does everybody see that we get a problem there? Okay, you're saying you don't see a problem? That's okay. What's that? When we were looking at this one, and we actually, I want those back. And we split, we had that positive and negative, and we said that could easily come from an alkene. There's our stable starting material. If we go through to look at the new system that you guys have now drawn, does that positive negative actually work out so nicely? I can't stabilize those easily. Okay? Is there something else that you could have done? What do you mean? We could shift the brackets to a different location, and believe it or not, you're going to end up with the exact same issue. What was your suggestion, Kayla?
No, two different monomers to make it diamond.
What if we said this in blue? Our positive, negative, and our positive, negative. Okay. Would it help if I got rid of some colors instead of doing blue, threw in a green for the second one? Or do you guys see that? This piece is here. This piece is here. So what I'm reacting now are two alkenes with each other. Kind of pick it up? Did the starting structure, so now can I erase all the stuff on the starting structure? Clean that? Okay. In this case, because I'm erasing it, I can't actually revert it. Well, no, I can because I'm erasing it, not just deleting it. If we look at that, it wasn't sass. That was me explaining. Come on.
I was there for the first year.
Oh, okay. That piece could have worked, but then we don't get a stable structure that we could have started this process with. Right? If we go the other route, what we're saying is that there's actually two repeating sections within this. And it's now how those alkenes react with each other. Kind of get it? So in our choice of a shorthand, which one was more correct? Again, IUPAC versus the world. Do we want to see where those pieces came from? This blue one is a much better representation of our repeating system because we can see where those pieces now came from. We're kind of reverse engineer what the pieces are. Make sense? If I want to follow some strict arbitrary rule system, then the purple one makes the most sense. Okay? With both of these polymers that we just looked at, notice that we started with what kind of starting material? An alkene. Okay? And ultimately a better description would be a non-polar pi bond. In the process of making the connections, the polymer backbone, the pi electrons were used to make that, which means every time I make that backbone, I lose a pi bond. What if I started with a triple bond? I would be left with a pi bond in the polymer backbone because I'm only using one pi bond to make each polymer connection. Make sense? Okay. In that process, what kind of reaction am I running? What happened to the pi bond? I broke it. So what kind of reaction? I'm starting with a pi bond and I end without a pi bond. That would be an addition. Okay? So if meant to ask, but I can revert it. Is that okay to erase all that? Okay. These two polymers both start with our non-polar pi bonds. Okay? And they run through an addition reaction. Let's take a look at the next one. What the hell? Oh, because I didn't fix that. There we go. Okay. So if we look at this one now in kind of the blue box, where's our smallest repeating unit?
From the carbon part. Yeah.
So I'm hearing that reference. Okay. Would red also work?
Yeah. We're just going in the opposite direction.
Purple? Yeah. So there's three different possibilities that could come out of this. Okay. This is going to be difficult because I've got all those colors on there, but I'm going to attempt to break those down into the individual monomers. Let's start with the blue. One of those would need to be positive, one end, carbon, or the nitrogen. Was my attempt at making those bold. One needs to be positive, one needs to be negative, just like with the addition polymer. Would I predict one of those to be positive or negative in increasing fashions?
The carbon's probably going to be positive and the nitrogen's probably going to be negative.
Why?
Because the carbon is attached to it nitrogen, and the nitrogen is more electronegative than carbon, so it just makes
And
more sense than having negative carbon and positive nitrogen.
Nitrogen probably has a lone pair of electrons. Okay? Could I foresee stabilizing that? Is it possible for the nitrogen to have those electrons under all circumstances? What circumstance would counter that?
If you put it in a very acidic solution.
Under acidic conditions, that would get protonated. Under every other condition, would I have electrons? Yeah. So having that nitrogen be negative or partially negative is very, very easy to do. Right? Could I have that carbonyl oxygen be positive? It's always going to be partially positive, but it can't go in as a normal positive. We could see this option of a resonance of the oxygen contributing down, right? But why is the oxygen contributing down? It would contribute down if the carbon was formally positive. But how did it get positive? How did it become formally positive? That's a hard question.
There would have to be no hydrogen.
There would have to be no hydrogen there so that it's formally positive.
Yeah.
So you're saying that fourth bond has to not be present. Would hydrogen have been a good place to start this?
Wait, what?
If there was a hydrogen there, is there a hydrogen in your polymer? No. So whatever's connected out there to temporarily stabilize that positive has to disappear from your overall structure. That would mean it would have to have left the structure, which would mean it would be a good leaving group. What would be a good leaving group that we could attach there? Halogens are fantastic for this. For those of you in the lab, we did it as an acyl chloride. Okay? For those of you that aren't in the lab but have some biological background, it could be an OH. Not a great leaving group, but it could theoretically work. I can throw on some hydrogens onto that nitrogen, and I now have an amine with an acid, and if we flipped it, we've got an amino acid. Proteins are polymers. Okay? In the course of this reaction happening, what occurred? Well, the next polymer gets aligned in the exact same location, right? This nitrogen has to come in and connect to that positive, ejecting the chloride, right? And then I'd also have to eject hydrogen. The net result is that I'm getting rid of a small molecule in that reaction. Okay? In this case, hydrochloric acid. So in this polymer, it is not following the basics of our addition polymer. Because our addition polymer was just a standard addition reaction with nonpolar pi bonds. How is this one right out of the gate different? It's reacting with polar pi bond. So in this case, we're looking for polar pi bonds to react. Okay? What kind of reaction are we running? That one becomes trickier. If we look at where the curved arrows are, we're doing a nucleophilic addition followed by a nucleophilic elimination or nucleophile elimination. So we could call it an addition elimination polymer. It's a bit of a mouthful. Where this reaction typically happens and where it got its name from was with that really bad leaving group of the OH. When I pair up OH with H, what do I get? Water. It's not an easy reaction to run. If it's not easy, what do I typically do? I heat it up. As I add that heat, when the water forms, because it's hot, the water turns into a gas. So I'm running the reaction, something's happening. In the process of that something, that I see this weird stuff evolve off. It touches cold glass, and I see condensation. The name of this polymer is a condensation polymer. Okay? The addition polymer is based off of the chemistry. The condensation is kind of based off of the chemistry, but that's more an observational name for it. Okay, kind of makes sense? So what we just went through and did was looked at what the monomer would be if it was in blue, and we came up with a legitimate potential polymer or monomer. What if we looked at it in red? Okay, where would my charges likely be? So we're looking at the red dots now. We need a positive and negative, just like we did with every other one. Positive on the carbonyl, very likely because
It's partially positive.
oxygen's withdrawing. That makes a lot of sense, which means the other carbon must be negative. Do I get negative carbons very often? No. So while that does show the repeating unit, does it give me information about the monomer? Not useful, which would mean that's probably the wrong pattern to find within that backbone. Make sense? Ish? Okay. If we go through and do it with the purple, whoops. What do we see? Kind of the same result. The nitrogen is very clearly negative. The carbon would have to come in as a positive. We had positive carbons before. This one's a primary positive. There's no nice stabilization. There's not even a strong electron withdrawing effect. That potential polymer repeat, while valid, doesn't give us information about the monomer. So with a lot of our polymers, what you are doing is looking at a polymer chain and trying to identify a repeating unit that allows you to come up with a monomer. How do you know where your repeating unit is? Okay. You'll notice the blue one worked right out of the gate. Probably an artifact of me trying to draw a polymer starting with the monomer. Okay. But if it was a half decently written question, you might see something like that, which means someone would very quickly jump to the red one, which resulted in a horrible monomer. Does that make sense? So when you're looking at a polymer chain, don't just think beginning and end. If anything, think dead middle. Where do I see the best system within this? Again, we're concerned about positives and negatives. So let's go back to our polymer structure. Where do you see potential positives and negatives through the polymer backbone? The nitrogen would be a really good negative. What else do we see? The carbonyl would be a really great positive. If I'm looking for my repeating unit, what I want to do is draw my repeating unit through the connection between the negative and the positive. That allows me to see that repeating system much quicker and more efficiently. I couldn't do that with the addition polymer. Why? They were non-polar, so I can't see those charges building up in the backbone. I can see it in this case because it's a polar backbone. Make sense? So a lot of what you're trying to do is find that shorthand, because once you have that shorthand, you can predict something about what your individual polymer or monomers are. Okay? Let's take a look at, I didn't mean to erase the condensation, so let's try that again. So let's take a look at another polymer. Oh man. Where's our repeating? So let's try the cheat. We had the cheat, right? Positive, negative. First thing we see is negative with the nitrogen. The next thing we see is negative. That should be sending up alarm bells. Why?
Because you have two negatives on the same end, it can't work.
We need to connect negative to positive, negative to positive. I have negative, negative. That doesn't align. Something's missing. What's the next thing I see? Positive. What's the next thing? Positive. I'm getting that exact same issue. Meaning, the connection I'm probably making is through there. Negative, negative, positive, through there. Right? Would that work as a potential? Yeah. But again, it has this negative, negative, positive, positive. That sounds like we could probably separate those compounds here. What does that mean? We have 2 monomers going into this one. Okay? It is possible, again, that it was one monomer, that it was one big long one. The more likely scenario is there's 2 monomers going in. Kind of make sense? Yes?
Because they will build up the charge on both ends, will they pretty much always react in this alternating manner?
So with the polar pi bonds, because they are polar, they are very logical and sequenced in how they alter through.
So they're selective?
They're very selective in that case. With the addition polymer, the one that I've now since erased, where we had something like that, where we had 2 different monomers. Everybody remember? What's that?
You get all sorts of combinations in that one.
Yeah. I'm not going to get red, then blue, red, then blue, red, then blue, because there's nothing to polarize that. I could get red, 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 followed by blue. It could be red, blue, 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 red. Okay? Kind of, sort of?
So polymer gibberish then.
Okay? The addition ones will end up with potential polymer gibberish. Addition, or the condensation, are very ordered because of that polarity. Okay? In our examples, these 2 have something in common. Fudge sickles. These 2 have something in common. And because this is extra clear and obvious, we might as well just continue to butcher it this way.
Which one is that supposed to be? Is that? So top and bottom.
Let's pause. Let's just pause for a second. Are you okay with all the language that's written on there and the notations? Yes. Okay, I'm going to clear all that away. No. We're going to do this. These 2 have something in common. We'll switch that in as black. And these 2 have something in common. So if you're taking good notes, you should be able to catch that commonality. Red was single monomers, blue had 2 monomers. Okay? We can reference those by different names. They're both polymers, and the red one's nothing really special, so we just call it a polymer. The blue one, because we're now using 2 different monomers in that process, we'll refer to it as a copolymer. Co, because together, you have 2 different things. Okay? Yes?
Is there any difference in name for selective versus non-selective copolymers?
Yes. Block copolymers versus copolymers, which I think I got rid of from the slideshow because it's not that big a deal.
So block is the one that selects?
Block is non-selective because you could get sections,
Gotcha.
all red, all blue.
Blocks of, okay.
Yeah. Okay. So polymer formation, we addressed this a little bit. We've got our addition polymers and our condensation polymers. The condensation went through nucleophilic addition elimination with carbonyls. So if you see a carbonyl, you know you have a condensation polymer. Okay? The addition polymers go through free radical addition polymerizations of nonpolar pi bonds. Why is it a problem to say alkenes?
Because alkanes can do it as well.
Because what can do it as well?
Alkynes.
Alkynes can also do this as an addition polymerization. Okay? So the addition polymers typically go through a free radical addition. They don't have to, but they typically move through free radical additions. The condensation polymers will always run the same general mechanism, nucleophilic addition elimination.
What if you have something that's non-carbon-carbon? Let's say like carbon-sulfur?
There are other types of polymers, and they're usually moving through some other kind of mechanism that isn't worth discussing, unfortunately. Okay. Usually those are three-membered rings. They're ring openings. Okay? So with the addition polymers, because they're free radicals, all the way back to semester 1, you should have had some information on radical reactions. Radical reactions get split up according to their mechanistic steps. You get initiation, propagation, and termination. Initiation. What happens in an initiation? You start it. Well, what's starting it? You're initiating a radical. So you're starting with no radical, and you now have a radical. Okay? Your initiations typically move through some kind of peroxy starting material. That peroxy starting material is the beginning of our chain. If we remember back, I don't think I referenced it actually names in the video, but since you all were here, Alex mentioned the CH3 with that polymer, and that CH3 didn't work because it didn't repeat through. That CH3 is effectively the initiator molecule. Okay? I don't care about that piece. What I care about is everything that happens afterwards. But that piece is what initiates the mechanism. Once I have the radical can go through a radical reaction with our alkene to form a new radical, which can continue on and on and on, propagating the polymer. Okay? So our propagation start with radical, end with radical. Eventually, I'm going to decide I don't want any more polymer formed, so what can I do?
Terminate it.
I can terminate it. I can add some kind of terminating molecule to this. That terminating molecule is not on the slides. Woohoo! But we would add something to go ahead and stabilize that terminal radical to kill the reaction. Then I could isolate the polymer stuff and do whatever I wanted with it according to its physical properties. Kind of makes sense? Okay. The condensation polymers, you're just doing condensation reactions. This was here so that I could draw a condensation mechanism. I don't really feel like going through and drawing all of that. Okay. We just talked about it in the last unit. If you need help with that, that's fine. I'll draw a mechanism for you outside of class. Okay. But nucleophile, electrophile, nucleophile, electrophile. Okay. Notice here, what are we starting with for our monomer? An alkene. So what kind of polymerization should we get? Addition. Should it be radical or something else? It's something else. And I know it's something else because what am I pointing to? Something other than a radical starting it. Okay? What is that thing that is starting this? An anion. It is a negative thing. So in the process of running this reaction, starting the polymerization, my polymer is going to continue to grow with a anion starting that polymerization. So this would be known as an addition polymer, but how was it run? Was it a radical polymer? No, it wasn't started with a radical. It was started with an anion. So I call it anionic polymerization or an anionic addition. Okay? Could I have started it with a cation? Yes. Okay? That is also equally possible. Okay? And so those separate categories are just kind of referencing how it was initiated. That initiation gets felt in the charge of the polymer growth. Okay? Crystalline solids versus amorphous. Your polymers are these long extended structures. You can get crystalline polymers. Okay? They're very rigid. Sometimes they're clear. Right? Versus amorphous solids. Those polymers move all over the place and don't form these nice crystalline structures. That's really all it's talking about. Right? So rubber bands are polymers. Which polymer do you think they are? They're amorphous because they stretch. That's the whole point behind them. Okay? As you stretch them, what's happening? You're organizing them, making it crystalline. When do rubber bands break?
When they're cold.
When you've made them crystalline. Okay? That's when you've broken that structure and you've now exceeded the strength of that crystalline interaction. Okay? Thermal transitions, you can reference them kind of on melting points, but because the polymers are generally massive mixtures, you don't get super clean melting points. Okay? So what you get is this transition point on your phases between solids to liquids. Okay? And that's all that this is kind of referencing is with our thermal transitions. You get the glass transition temperature. Not a big deal, don't stress about it, but Cardi mentioned it. It's kind of a neat concept, so I threw it in there. But that was it. Okay? Do you guys have any questions about polymers? And this is literally just the slide out of Cardi's stuff. Okay. Where that takes us, come on now, would be to just review. Okay? So I picked these out a while ago. Some of these involve polymers, some of these don't. In fact, only one of them involves a polymer. Okay? Do you guys have specific questions you would like me to look at? Or do you just want to kind of work through these and see what you can do? Work through these? Okay, so let's put it this way. You've got 5 questions. You're supposed to get 1.5 minutes roughly per question. So what is that, 7 minutes? All right? So I'll time you. Do as best you can. So you do not have to take my word for this, so you can decide that I'm just making it up. I intentionally have not looked at these questions. Okay? I did do a quick scan over them to see if they were all polymer questions, and that was about it. So I've not actually read in detail any of them. Full disclosure, the upper left-hand corner, I have read rather extensively because I copied that question onto one of your exams. Okay? So I have done that one significantly. Okay? The next part that I really kind of want to emphasize will be just kind of a bit of a test. So I wanted to provide some context behind my sort of lack of knowledge of what the questions are themselves. Okay? The next part that we'll get to is throughout the semester, I have told you that what do you need to do? Draw. You need to draw and write down work. That improves your odds. And consistently, the response I get back is, I don't have time. Okay? You're wrong. Okay? The reason you don't have time is the exact process that you guys all just went through right now. You sat there and you stared at the question. You're like, how can I solve this? But you didn't write anything down. So you wasted, and the amount of writing that happened across the board, maybe it looked like 2 questions were attempted with actual explanations behind them. Okay? So in 7 minutes, if we just look at that, you wasted 5 minutes of just staring blankly at stuff without trying to write some information down. That information you write down can help you interpret the questions to move forwards. If you don't put that interpretation down, you are constantly doing that interpretation in your brain, which means you increase the odds of doing it wrong. Does that make sense? Okay, so to that end, we're at 44:15. I will go ahead and start. I want a product. In this case, I've got a negative. I need to find a positive. Negative to positive, tack, comes back down, ejects. I'm going to get the CH3, C double bond O, OH. The other half will be this O18, CH, CH3, CH2, CH3. They say the R stereoisomer, the R is referencing the position that has 4 different carbons. or 4 different things, I should say. There's a carbon with hydrogen 1, carbon 2, carbon 3, oxygen 4. The 2 and the 3 are different because this is a CH2, this is a CH3. So my chiral atom is that guy right there. It had nothing to do with the chemistry of the reaction whatsoever, which means if I started R, I end R. Other pieces I missed here, I didn't actually specify what that came in as, so that's really just a negative. I can go through and look at my pieces. CH3OH, wrong, wrong, possible, possible. The rest of it is the R. There's R, that's S. Answer is C. What's that? It's not that it starts R and ends R. It's that the chemistry that I did nothing to the stereocenter. That's why it ended the same. Okay, and so that's one of the misconceptions is people will push as, oh, it's doing inversion or it's doing retention. That's the wrong direction. Nothing about that stereocenter had anything to do with the chemistry. It's irrelevant to the question.
Would they do something like basically the C and D answers, but with an acid versus the deprotonated acid? To test that?
Oh, good point, because yeah, if you look at what I've got here, I put the H on there, and they didn't put the H on there. It doesn't change the answer, it's just changing the protonation states. Okay? Could they have shown C, but with CH3CO2H, and then the R isomer? Yes, that would have sent up all sorts of red flags, though, because what would I have done? CH3CO2H and R isomer. I have 2 answers that are now tying to the exact same match. Now I have to look more carefully at the protonation states to decide. Make sense? Yeah. Okay. Next one. Intermediate, probably charged. Base promoted. Base is negative. So I'm going to quickly look through what the hell. Intermediate involved in the base promoted hydrolysis. The negative comes in and attacks, goes up to form the negative charge. Yeah, that's actually right there. There it is, C. I had the answer before we had any chemistry actually done. What monomers are needed to produce this polymer? Positive, positive. For the record, this positive-negative thing that I'm doing right now just showed up in this class period. I've never done that before or seen it. There's my positive negative. If I copied and pasted outwards, I'd get the negative going this direction. So I'm looking at these 2 pieces. So I need my positive structure with 2 carbonyls. No, 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 possible, possible. The other one had 2 negative oxygens or 2 oxygens at the end. Yes, 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 shit. In the blue one, I have 2 carbons in between. In the red one, I have 2 carbons in between. Whoa, come here. This has no carbons in between. This has 2. That has a hell of a lot more than 2. Answer's D. Knowledge of base strengths. Base is negative. Predict which of these reactions would be most likely. So reactions likely to occur. So if I'm going to go this way, I want my biggest negative over here, my smallest negative over there. It's a partial negatives. Right? Okay. So if I go through and compare negative to negative, negative oxygen, this one does resonance more stable. Doesn't match my pattern. Negative, but we have oxygen versus chlorine. Same charge, size, chlorine's larger, chlorine's more stable, doesn't match my pattern. Negative, oof. Negative, negative oxygen to negative oxygen. that becomes challenging, so we'd move to resonance. This one does have resonance, which would suggest this is more stable. This is possible. We move to the next one. I don't see any charges. So if we're going to have to address that, my negative is the sulfur versus the nitrogen. Sulfur is larger than nitrogen, making it more stable. Answer C. Structure is a reasonable intermediate, looking for charges again. Acid catalyzed being positive. So I want positive structures, bad. Okay, now looking at this, that's just awful. Okay, that's a bit mean because that is now experience, crossing that one out. Okay. The next part, let's see, positive oxygen, what the hell? B. Time 51:06. When did we start?
47 something.
47 to 51. What's the deal with the timing? I hear you. 4 minutes withdrawing. How many of you got all of the answers right? You had 7 minutes and you did no drawing. Do you have time to do the drawing? Yes. Okay. Drawing is important. Does it look pretty? God, no. Okay. All of that, though, you're trying to keep in your head. That's why you're getting it wrong. Write it down. Okay. So I will answer. I'm not ignoring you, but I do want to address some other things with this. You're not allowed to write in the test books. This is why you're having or being given scratch paper and tracing paper. So you can put tracing paper directly over each page of the exam, and you can now write in the exam over the top of it. Okay? That way nothing makes it into the exam. ACS doesn't get pissed at me. You also get the benefit of being able to just copy directly over the top. Okay? A lot of what I wrote wouldn't fit in the exam anyway. Right? Okay? For reference, I do go back and look at work, particularly if you're a borderline grade. I will go back and look to see, what did you write? Did you give me some evidence that you've learned content this semester? Okay? So I will go back and look at that work and be like, is there something to show that you actually know this and you deserve that higher grade? Okay? If there's nothing there, you've given me nothing on which to make an argument for a higher grade, and you're stuck with the lower grade. Okay? So putting some writing down can help. So you'll get tracing paper, you'll get scratch paper. The other thing that can be helpful is going through, as you went through, I crossed stuff out, right? It was like, this is wrong, I don't want to look at this. You could do that on tracing paper, that's kind of a waste of space. I will also give you 1 through 70, okay? Print it out with A, B, C, D next to them. As you go through and do questions, you can cross stuff out. So let's say you started going through and you're like, I know this one's wrong. You're like, I have no idea what else. Move on. You now have a track record of knowing that that answer choice is wrong. When you come back to the question, you don't have to reevaluate that. You already know that one's wrong. Answer one of the other choices. Does that make sense? So you will have lots of paper in front of you. You should try and take advantage of as much of that as you can. Okay? Well, I believe your question was the last one, the experience. I'm going to say a couple things with this. Okay, so number one, having that positive charge on that carbon is questionable for the ACS because that's a bad Lewis structure. Why is it a bad Lewis structure? Octets. That carbon doesn't have its octet. So to have an intermediate, and particularly a reasonable intermediate, it should be a good Lewis structure. Okay? So I will fully admit, my reflex to crossing it out is a reflex. I didn't process, that's a bad Lewis structure, it says intermediate. That is just my reflex. Okay? So some things can be improved with reflexing on getting rid of answers. The next part that would kind of push beyond this is you'll notice for that question, I didn't actually dig into what the question was asking. Right? I really just said big bullets. Intermediate, charged structures, acid catalyzed, it needs to be positive. Which of these matches those patterns? Okay? So let's say, you know what? I didn't have that experience. Okay? Does that satisfy that positive? Yes. So I now have two choices. How could I go through? Can I erase all the other stuff? How could I go through and resolve away those two choices? Which admittedly I probably should have done, so I apologize. Right? I still think I would have finished before 7 minutes. Ethyl acetate. Okay? So now I have to know nomenclature to answer the question. CH3, CH2, CH3. Do I know nomenclature well? No, but what do I do know? Where charges fall. I get through the question without having to answer anything about nomenclature. If you don't have that experience or that process that I've been telling you to push to dealing with those charges, you have to pick it up somewhere else. The nomenclature can help. They now say dilute aqueous acid. So we've got H plus floating around, and if it's aqueous, I have H2O floating around. Okay? In this process, I see a carbonyl. That should be sending up alarm bells that I should be doing some kind of reaction with the carbonyl. That carbon is positive. Okay? The next kind of piece I should see, that oxygen is a potential leaving group, making that carbon even more positive. I would need a nucleophile to cause that leaving group to come off, because that's a crap leaving group. Water could come in and attack. Right? That would be fantastic. This would break the pi bond. That, unfortunately, would put a negative charge on that oxygen. Can I do that? No, because it is acid catalyzed. How could I minimize that negative charge? Dump the positive on first, then do the attack. Okay? The basics of what I had written down already eliminate D, because I can't have that leaving group leave on its own. So D would become wrong. I've got B without actually even drawing that structure. Does that make sense? Okay. And I will fully admit there's a lot of comfort that I have behind this and that knowledge of where everything is, but you should be making those steps to trying to match that. Okay? That means drawing it out and drawing reflexively right away. As I read the question, I was taking notes. Okay? Not reading the question, then taking the notes. Okay? We're saving time. How much? What was it, 4 minutes? That was a pretty significant save in time. Make sense?
Yes.
Okay, yes.
I had a question about
The one I erased? Top right? Okay.
the base string.
Yeah?
I thought that the rolling of bases isn't, I thought sulfur being lower was negative. Like nitrogen is more electronegative than sulfur. I know it's bigger.
Fantastic. Nitrogen is more electronegative than sulfur, so shouldn't it hold its electrons tighter, thereby making it the weaker base? Where's electronegativity in our list of things to evaluate? Charge size. Did you say electronegativity? No, so I don't care. Size. Does that make sense? That's why those rule sets are there.
Okay, so where are you gonna be on Monday or Friday?
Tutoring Center, Library 228, which is also where I think I'm going right now, or right after class, officially. As far as ACS study guides, I thought I had a whole bunch in my office. I can't seem to find them, so I think I took them home. So I will be looking for those tonight to be carrying around with me. The Tutoring Center does have several. Time for Friday, the Tutoring Center, I believe, opens at 8:30. I will get there as soon as I get to campus this Friday. Same deal for Monday. I go to my office, depending on my mood, maybe I'll dress up, or maybe I'll just go in my dad clothes. What's that? Yeah, that's fine. You can work by helping your classmates.
I think on their website they have like one practice section.
I don't think it's free. I think you have to pay for it. If it's free, great, use it.
The first one, yeah, they have one.
Yeah. My experience with what they've offered, and I'm going to stop recording.